Okay, and continuing our theme of borrowing for the session, we have Sidney Congard.
Yes, thank you. So hi everyone. Today I will speak to you about linear functional translation for borrowing. And so to give a bit of motivation, I'm a first-year PhD student, and my goal is to study programming languages in which we have resources by translating them into a pure linear and functional language. And so resources can be like memory allocations, files, sockets. So it's a kind of ubiquitous notion in programming language, and they require special care about bad behaviors. So typically, if I use allocated memory, I don't want use at the free, meaning freeing the memory, then accessing the memory. And so in this talk, we'll focus on the notion of mutable borrows. So that was already presented just before. So those are exclusive read-write accesses to a value. And the plan for this talk is to first look at the proofs of non-aliasing that we get from the new Rust borrow checker, which is called Polonius. And then we will look at how to interpret them functionally to obtain the translation. And so this work is largely based on Aeneas. So it was one of the papers that we saw before. So if you know the framework Aeneas, several things should be familiar to you. It's a framework that translates safe Rust programs to pure functional languages. And this is very much a work in progress. So for now, the work done is a paper proof of adequation between the imperative semantics for the language and its functional translation for a small fragment, so with Boolean function pairs, mutable borrows, and so no inference, not trying to infer the lifetimes, so similarly to the previous talk, and for now without region constraints. So we will see a bit what all this vocabulary means a bit later. So we heard this Rust slogan before. So this is the invariant, indeed, that we want to maintain during our whole program. And because we only care here about mutables borrow, it means that only the most recent read-write access to a value must be available. So for that, I wrote a first program to illustrate this. So if I declare an integer a, then borrow it. So I have this read-write access named b. Well, I have a more recent access that I can modify my integer through. So here I increment it. But then if I want instead to access a and not b, because a is not the most recent access to the value under a, I must first invalidate the access to b. So I write that by it's called dropping the borrow b. And so this ensures us that at this point in the program, at the assertion, A remains the more recent access to, well, in this case, A itself. So if we try to access B afterwards, we get a compilation error. So now that we see this invariant, we will work by example to understand how the borrow checker can guarantee us that. So to begin with, I will work through a naive program. So this is a function that consumes 3 mutable borrows and a Boolean and returns either the first 2 borrows or the last 2 borrows. And to use this function, I can declare 3 integers, call this function with the 3 borrows on each integer, and I get back 2 new borrows through which I can modify my integers. Then I can read the updated values from of my integers. But here, f does not compile if we put that into Rust. And so we need to understand what information the borrow checker needs in order to ensure the invariant I explained before. And so for that, we will understand how the borrow checker thinks, at least the Polonius borrow checker. So it does not think in terms of lifetimes, but regions. So to each borough, it will associate to its type a region A, which is the set of possible values that are being borrowed. So the larger the set is, and the less precise the region is, because we don't know among many values which one is the one currently borrowed. So I will write B colon A to say that the borough B is associated to the region A. And so now our mechanism to ensure the previous invariant is that if I want to access any value V, I first must end all the regions that contains this value. So I will say everywhere where this value may be borrowed, I want to invalidate those accesses to remain the more recent access. And so to end a region, we must simply invalidate, drop all the borrows associated to this region. So with that, at the level of types in our program, if we look at the type derivation of our program, this yields a proof of non-aliasing for our access. And then we want a modular verification, meaning that if I write a function call, I don't want to depend on the body of the function to basically type check the program. So all the information about the regions must be contained into the function signature. So now, to correct our previous program, we will simply, for now, add a region parameter that I write A with the tick. And so what that means is that as I associate all the input, the borrow inputs, and all the outputs of this function to the same region, saying that everyone may alias the same set of possible values. So each borrow has a different value among those possible values. So now, if I follow, as before, the execution of my program, when I call f, my 3 newly created borrows must be placed into the same region. So I end up with a new region A, which contains the 3 integers that I declared before. And so after calling f, what I have in my context is this region A, and the 2 outputs borrow, S and T, that are associated to this region. So at this point, I know at the level of types that S and T may alias either U, V, and W. So after that, I can, as before, modify my integers, and then when I want to read U, I apply the mechanism I described before. So I say, okay, I access U, I check what are the current regions in my program, so A, and because A contains U, I want to end the region A, and so drop all the borrows associated to A. So I drop S and T, and after that, I'm guaranteed that U is the most access recent, and so the only access to himself. Okay. So now that compiles, but if I want to be even more precise and say, okay, let's just modify S first, then access U. Then after that, I may want to still access T, and finally read my 2 last integers. So as we saw before, if we read U, we must invalidate our 2 borrows. But if we look back at our function, so if we look back at F, we see that its second output will never give us back the first borrow. It's either the second or the third borrow. So in fact, we know that the second borrow never aliases U. So we want this program to be able to compile. But for now, the borrow checker doesn't have enough information. So how do you explain to the Rust borrow checker that T does not depend on U? Well, we have region constraints, which are also called lifetime bounds. And so this allows us, when we declare new regions, that says that one is more precise than the other. So if I write A0 colon A1, it means that A0 is included in A1, meaning that, well, A0 is more precise than A1 because for whenever I want to access a value in A0, I must end A0, and so I will also need to end A1, because A1 also encompasses all the possible borrowed values from A0. So don't hesitate to ask if this is not intuitive, because I think that's one important bit. And when we have this definition, this allows us to convert a borrow associated to the more precise region to one to the less precise region. So in this case, going from A0 to A1. So once that we have that, we can complexify a bit. Okay. There is nothing after the T. We can complexify a bit the function signature by splitting the output into two different regions, A and C. So then, when I invalidate one, I may not invalidate the other. And so for that, we know that the first input must be convertible to A, the second input must be convertible to A and C, and the last input must be convertible to C. So for that, the first and last input, it's quite simple. You put them into the same region. But for the second input, Y, we can say that its region is actually more precise because it's included into the region A and C. That's why then we can convert Y to either the region A or the region C. So that means that the region B is included into the intersection A and C. So now if we follow the execution of our program one more time, I have my integers, and when I call the function, I won't build the same regions. Now I build those three regions, so A, which has the two first inputs, B, which is only made of the middle input, and C, which is made of the two last integers. And now that we are at this point, we know that S is associated to A, and that T is associated to C. So if I want to access U, I only need to end the region A, because U belongs to the region A only. And so for that, I only need to drop the first borrow S, and I can access U. So after that, I can access T again, modify its integers, and finally read the values of V and W, and that will ask me to end the two other regions, and so drop my last borrow. And at this point, we have finally everything we want to know about Rust borrow checker Polonius. Because this compiles, it's fine. So now, what we want to do is to take a program that is borrow checked, that has all the annotation in its type derivation, and interpret functionally those proofs of non-aliasing to obtain a linear program that will behave the same as our starting program with its imperative semantics. So for that, we have this correspondence that I read that, which is quite high level at this time. Each region made of borrowed values, possibly borrowed values, and associated to borrow Y, will be translated to what I will call a root, which is a linear function that consumes the borrowed values and will give us back the values that are possibly borrowed by those arguments. And so if you know Aeneas, this corresponds to backward functions in their paper. So then a borrow is translated to its underlying value, so we keep the mutable state of our program local. And then when we drop a borrow, we will simply pass the value borrowed to its associated root. And finally, when we end a region, it means that we first get all the arguments of the corresponding root by dropping the associated borrows, and then we can call the root to get back the values that have been borrowed. And finally, the dependency between regions, by saying that one region is more precise than in the other, is translated by a functional dependency, meaning an argument that flows from B to A. So it means that we must end B before C, before A, sorry, in the left column, and in the right column, it means that we must call the function B to give back the dependency needed by the function A to call it afterwards. And so now I will process on the previous examples to see how the signature of a function is translated. So the idea is that a root A associated to the three inputs X, Y, and Z is associated in the output to the two output borrows. We translate that to a linear function that we get in the input of our function that will consume those three values, X, Y, and Z. And then in the return type of our function, we'll get back another linear function which corresponds to the same region A, and so gives us back the same possibly borrowed values. But at this time of the program, it will only consume the remaining borrowed associated to it, which are the two outputted borrows. And in fact, we have an isomorphism of types. So if we just inline A with the identity function, so it means that we associate to A the smallest possible regions. We get back a function that takes back, that consumes the value of the borrows and gives us back the output borrows values, along with this function that will consume the borrowed values and gives us back the updated values. So this is very similar to lenses. And then, once we understand this mechanism, we can look at our second signature where we needed to support region constraints. So the idea is that we look at the dependency graph that we get from the previous function, so consuming the two outputs, giving us back the three inputs, and adapt it to those new regions. So we saw that the first output is associated to A, the second to C, and then that B is included into A and C. And that was translated by a functional dependency. So from the function signature, we don't know the concrete type that may hide behind this functional dependency. And then for the output, we have our three borrows, each associated to its own region. So by the same principle, if we translate that to our function signature, we have this function that consumes the values, gives us back the values, and the three roots that correspond to each region. So once again, if you have any question about the correspondence for the function signature, don't hesitate to ask. And so once that we translated the function signature, we can look at how it's used at function call site. So if we roll our translation through the starting program, we first declare our three integers. Then when we call the function, the borrows are just the underlying values. And so S and T are new integers. And we get explicitly the root that corresponds to each region. So then we can modify the integer directly. And finally, when we want to access U, ending the region S corresponds to calling the root S with its argument A. And so we get back the updated value of U in a functional manner, and also getting this, dependency for the region B. For now, we don't know what is hiding behind it because we didn't see the implementation of the function yet. And after that, we can modify T. And when we want to access our two last values, we want to end those two roots. So first calling the function C, getting back the updated value of W, and then getting back the second component that is needed to call B. So we have R0 and R1. We can end the region with those two. And finally, get back the updated value V. And so the assertions are only there to demonstrate the state of the program at each step. And so now we translated our function call. For the function body, I will not go into much detail for the translation. The main idea is that when we do borrow conversion, that results into losing some precision about where is the value given back. In the functional translation, it would correspond to passing dummy values around. So if I have two roots, two functions, I will add a functional dependency between them. And so we can see in the body of the function that we have some unit values there that represent those dummy dependencies. And because we hide them between existential types, this program is well-typed. Because we see here, for example, that in the first branch, we return a unit type, and in the second branch, we return the real dependency, so the underlying integer. And so we see that for the region B, the concrete value comes either from the left or from the right. So in conclusion, this was a quite high-level view of the translation. So I hope I have enough time for questions, if you have. And for future work, what I'm looking at currently is how to exploit the linearity for resource handlings. So this is in work with Guillaume Munch, which has nice models for that. And so the idea is that once we are into a linear functional language, we are able to exploit that to speak about typically values associated to destructors and how they interact with exceptions and other effects. Then one other point is to delimitate the correspondence I showed you. So it's because if we want to have this functional translation available, we must be quite careful about the borrow checker inference rules. Because when I presented the roots, I presented them into an extensional way. So saying, for example, a region is a set of value, but then if we have two regions that share the same values, they will need to share them through a new common region. And if we follow the borrow checker, it's actually in this way that they are built. Like bigger regions are built out of like previous region. Also, if we want to preserve linearity, we have some restrictions on signature equivalences in Rust, because in the signature we see an explicit graph of dependency between the inputs and the outputs. So it means that we need to normalize a bit the function that we obtain and which describe the dependency within our program. And finally, it remains to explore more explosive borrowing because typically nested borrows, so borrows of borrows, having polymorphism, and the one which I think is like important but also may require a form of dependency is some types, meaning I can have a borrow on one region or a borrow on another region. So yeah, a lot of work to do, and this is all for me. Thank you.
Okay, are there any questions first? Yeah, go ahead, come to the middle, please.
Okay, yeah. I was wondering, when you have a type in Rust that contains a mutable borrow, how do you translate that? What do you put inside the type?
Yeah.
What's the data that's inside the type?
Okay, so the data is just not just the Rust program inputs, but basically, I don't consume for now I don't have an implementation of that, and what I consume is a more functional program, like I said before, that has mutable borrows. And so in this program, we have a similar program with Rust, but importantly with all the annotation from the borrow checker. So we really need them to not do the job of inferring all the information about regions. This is kind of what does Aeneas, actually. Aeneas consumes the Rust program directly. In this case, I simplified the job of not inferring the annotations. If
What I meant was, is the function, the root, is it completely stored inside the type? If I
the falsity. Oh, sorry.
Okay, you do translate types to functional
Yes.
programming, right? Inside that type, if I have a mutable borrow, will the entire root or the entire update function plus the data and that kind of stuff be stored inside the type?
Okay, so it's okay. So the whole secant change because we change the context to have those roots. So it's still modular, but it's not like type by type, and instead on the whole secant that we have the translation. Okay. So if I have one borrow at some part, the sequence change to be able to get the corresponding functional function, sorry, that consume the underlying value of this borrow.
Okay. Okay, thank you.
Okay.
Okay. I noticed that you didn't have immutable borrows in the future work. So is there a reason for that? Is it easy? Is it obvious how to do it?
So emulating
immutable borrows. Do you have
yes, immutable. Okay, so right. I think they are easier for this kind of functional translation because they don't require actually threading those value around. So really, what we have, or how they can be implemented, is more as a compile time reference counting. But for mutable borrows, we need to thread the values along, not just copy and then forget them. Okay. And so this is what adds much of the difficulty if you want to stay fully functional. Okay. This is why also I start from Aeneas, because the other semantics are more like, as we saw before, separation logic or other framework that may avoid this problem.
Okay.
Hi, can you say a little more about signature equivalence? You mentioned that you need to normalize things. What happens if you don't normalize things?
Yes. Do I have the simple example? But it should be. I will try to describe it by hand, but it's better to see them in graphical form. Basically, there is a tension between like the precision of the borrow checker, where we want to have a lot of small little regions, and a nice translation where we group together those regions. I have a few nice big regions.
So this is for efficiency. Then you want to reduce the number of regions.
So there are the two. There are the two regions. There is still another problem, which is that if I take, for example, the swap function, the may swap function. So it's no, maybe I don't have it on the other hand. It's a function that have two regions. A single region, and it may or may not swap the two mutable borrows that we are given. And so this is the most, when we see this function, we could write it that way, but we could also write it in a very more complex way by saying that I have 4 regions, like 2 for the outputs, 2 for the inputs, and then saying that the input region are included into each output region.
So for this function, a single region should be enough, right?
Yes, right.
Mm-hmm. But this sounds exactly like simplification in polymorphic subtyping, right?
Yeah.
When you infer polymorphic type scheme with subtyping, you also want to simplify these types to remove as many type variables as possible.
But then we need so we can, in this case, we can simplify the 4 region to a single one. Mm-hmm. But if we have like a big function that then use the may swap, the 2 different may swap. So for example, so we get basically we have may swap 1, may swap 2 that are used at the same time. So we have 3 borrows, and we may swap the first 2 or the last 2. Mm-hmm. We get an issue of confluence that it seems to me that is not. I don't think there is a general solution for this issue. So it means that if we want to stay fully linear, we may have Rust function which we can type into different way, and which can call, in which the one can call the other, and that we don't have this equivalence in the sense that one will not be able to call the other, even if they are equivalent in those. It's very weird examples. Like the simple example is with like 6 regions or something like that.
Okay.
That I found, at least.
So you just,
Okay, I
conclude-
do have to cut it off there because it's time for lunch, but
yeah, we can
keep it going offline.
can speak about that.
Yeah, thank you, Sidney, again.